Today we are ready to solve another applied optimization problem. This one is rather practical in nature as it involves optimizing a common everyday object, namely that of a cylindrical can. So here's the statement of our problem. We want to find the height and base radius for the closed cylindrical can having maximal volume given that its total surface area is to be 16 pi square centimeters. So as in the previous problems in optimization that we solved, our first step was generally to draw a diagram to determine the relative variables and their relationships. So in this case, our starting point is the can, right? So we know it's in the form of a circular cylinder with a closed top. Okay, so we'll indicate top here is closed, and the dimensions of interest, of course, would be the height of the can, we'll call it h, and the base radius, let's say, is r. Okay, so what was the given constraint in this problem? That was on the can surface area, right? Was that the surface area must equal 16 pi square centimeters. Okay, and so let's think about what that says about the relationship between the radius of the base and the height of our can. So it's telling us that 16 pi square centimeters is going to equal to the sum of the area of the base of the can, which is a disk of radius r, plus the area of the curved side of the can, which, if you think about it, if we would slice the can down with a cut that's that's parallel to the height of the can, we would flatten it out to obtain simply a rectangle, right? Where the width of the rectangle is going to be h, the height of the can, and then the length of this rectangle would have to coincide with the circumference of the base of the can, right, being 2 pi times r. So this would be the area of the side of the can. And then, of course, there's the top of the can, which again is a disk having radius r. Okay, so adding these three areas together, we must end up with 16 pi square centimeters. So that is, 16 pi is equal to the area of the disk, pi r squared, plus the area of this rectangle is going to be 2 pi r times h, plus the area of the second disk, which again is pi r squared. So we could simplify a little bit on the right side of the equation. Pi r squared plus pi r squared is 2 pi r squared plus 2 pi rh. Okay, so that would be the constraint. Now clearly on the right side, if we wish, we could factor out a 2 pi, and then the remaining factor, r squared plus rh. And now we notice we could divide both sides by 2 pi and end up with the relationship that 8 must equal to r squared plus r times h. So we have this one equation that relates r to h. Let's call this equation 1, given that our cylindrical can has a surface area of 16 pi square centimeters. Now, what are we trying to do in this problem, of course, is to optimize, to maximize the volume of the can. So let's write that down, right? The quantity to be optimized is the volume, right? And the volume, of course, of the cylinder is going to be the area of the base times the height, right? So this is the product of the base area with the height. So in our case, that would reduce to the formula for volume as being pi r squared, the area of the circular disc, times the height, which is h. Okay, so this we'll say is our formula 2 for volume. Okay, so very good. So we know that this is the quantity to be maximized, and again, as it currently stands, the volume is expressed as a function of the two variables, the base radius and the height. And so in order to use our analysis of derivatives, we would like to express the volume as a function of a single variable, right? But again, we could come back to equation 1 and use that to easily express the height of the can as a function of r, the base radius. So let's see if we could do that now up here. Okay, so now we're going to take equation 1 and we'll say let's solve equation 1 for h to get. Okay, so again, remember that this was equation 1. 8 equals to r squared plus rh. So we'll subtract the r squared from both sides. So we'll have that 8 minus r squared equals to r times h. And then simply now divide both sides by r. So thus, h must equal to 8 minus r squared all divided by r. Okay, so let's call this guy equation 3. Okay. Now remember, you know, when we're going ahead and solving these sorts of optimization problems, we also said, you know, it's important to keep in mind any necessary bounds on the ranges of our variables. Of course, h is the height. H is the height of our can. H must be positive. So let's just indicate, of course, h, the height, must be positive, and r, the base radius, must also be positive. But we notice that in order to keep h positive, r squared must be less than 8. So r itself must be less than the square root of 8. Okay, and of course, these are measured in units of centimeters. So now what we'll do is we'll substitute for the height of the can in terms of r into our equation 2. So therefore we'll have the volume as a function of only r. Okay, so that's our next step, is to substitute for h from equation 3 into 2 to find that the volume as a function of r will be pi r squared times the 8 minus r squared divided by r. Now, of course, you could see we could cancel one factor of r from numerator and denominator, and so simplify our volume formula to be pi times, let's say then we distribute this factor of r across this second difference to get 8r minus r cubed. So that, we could say, is now our formula for volume, expressed only as a function of the radius of the base of our can, where r itself has to be positive and less than the square root of 8. So now this was the hard part of the problem, essentially was setting up the problem, and now we just have to use our calculus, right? So the thing is to find where the derivative of volume is 0, right? To find that critical number. So dV/dr would be, right, because this is use the formula for the constant multiple rule, right? Derivative of a constant times a function is going to be the constant pi times the derivative of the function 8r times r cubed. So the derivative being 8 minus 3r squared, right? And we see that pretty clearly, right? dV/dr will be 0 if and only if 8 minus 3r squared is equal to 0. So that would mean 3r squared would have to equal to 8. Or we could divide both sides here by 3. R squared is 8/3. So that means that r has to be the positive square root of 8/3. Right? Of course, the units here would be in centimeters. Right? And of course, we know, right, r is positive, being that it's measuring a base radius, and lengths are positive lengths, of course. And so there it is, and so that's our critical number, okay? And we use that critical number to split the range of r, which was between 0 and the square root of 8. And the square root of 8, it's roughly 2.8. Okay, the square root of 8/3 is about 1.6. So 1.6 would be like 4/7 of 2.8. So like 1, 2, 3, 4, 5, 6. So it would fall in around here on our number line, the square root of 8/3. It's about 1.6. So and so that of course splits the possible range of r into these two intervals, and we would see that if we examine the sign of dV/dr here, whenever r is a number between 0 and root 8/3, so for instance, if r was 1, for instance, right, the derivative of volume would be pi times 8 minus 3, or 5 pi, right? It's positive, right? A positive derivative, again, indicates that the volume function has positive slope for r going from 0 to root 8/3, and therefore the volume function, right, is increasing on the interval from 0 to root 8/3. Okay. However, what happens when r exceeds the radical 8/3? We look at our formula for derivative of volume. For instance, if r was 2, then of course our derivative of volume would be pi times 8 minus 12, right? Minus 4 pi, right? A negative derivative, right? So that means the volume function has negative slope on this interval. Therefore, the volume is in fact decreasing on the interval from root 8/3 up to radical 8. And so what does this imply then about what's happening to volume when the radius of the base is radical 8/3? Well, of course, if our volume function was increasing on the left side of the point and decreasing on the right side of the critical point, then of course we maximize the value of volume when r was exactly the square root of 8/3. So therefore, we can conclude that the volume is in fact maximized when r is exactly the square root of 8/3 centimeters. And so then what we do is we go back to this equation 3 for the height of the of the cylinder, and so equation 3 tells us that the height is going to be 8 minus the r value squared, which would be 8/3, divided by r itself, the square root of 8/3. Now, of course, 8 is equivalent to 24/3. So let's say we replace the 8 by 24/3. So we get 24 minus 8 over 3, all divided by radical 8/3. So that, of course, would be 16/3 divided by the square root of 8/3. Well, of course, 16/3 is 2 times 8/3. So let's say we rewrite that as 2 times 8/3 over the square root of 8/3. But 8/3, you could say, well, that's like the square root of 8/3 squared, you know? So it's like 2 times the square root of 8/3 to the second divided by the square root of 8/3. Thus, we could cancel a factor of radical 8/3, and we see then that the height of our optimal cylindrical can has height equal to simply 2 times the square root of 8/3 centimeters. Okay, so notice what's significant here is that the height of our can is exactly twice the radius of the base in case we have optimal volume. So that is in fact, you know, a significant point. Okay, so now let's just you know, let's just write down that detail and complete our analysis here. So thus we'll say, right, the volume is maximized when the height of the can is equal to, well, twice the base radius would also be the diameter, right? The diameter of its base. Okay, and so so in the picture here, if you would think of kind of starting out just drawing a square, you know, so let's say, you know, this dimension, you know, this, which is also going to be the height of our can, right? And let's say, you know, kind of have, this is going to be, you know, the diameter of the base of the can, okay? And so we could sort of form our can, and this would be the relative dimensions, okay? So the diameter here is equal to the height of the can. These would be the dimensions for optimal volume. And this would actually be kind of similar, you know, when they, you know, used to have a lot of tin coffee cans when people would buy their coffee, mainly as ground coffee in cans. They were often roughly in this dimension of the height equal to the base diameter. And this would be, in fact, true in general. In other words, in general, the closed cylindrical can having, let's say, the surface area, just some arbitrary surface area, call it capital S, okay, and a maximum volume, will always have the dimensions, okay, that the base radius, which is our variable r, okay, equal to r, is always going to be the square root of whatever the total surface area is divided by 6 times pi units, and the height of our can is h, right, is always going to turn out to be twice r, or in other words, 2 times the square root of s over 6 pi. And you could kind of see that's true if we go back to the problem that we had just, previously solved. So in that context, the 16 pi, that would become our s. And so when we relate r to h, we would have had s divided by the 2 pi. That's what the 8 represents, like the total surface area divided by 2 pi. And so again, in this equation 3, the 8 here represents the s divided by 2 pi, and so on. Again, 8 here in the volume form, that would become s over 2 pi. And so solving for the critical value for r, we'd have s divided by 2 pi divided by 3, the square root, which would correspond to this value that we had here, the square root of s over 6 pi. And then going back, using that equation 3 to solve for h, okay, once we know our r, we'll find that, again, in general, the height is always twice r. Okay, so that was one sort of problem that we could solve for maximizing the volume of the closed top cylindrical can. So you might just wonder, well, what would happen if we solved the problem of optimizing the volume of an open top cylindrical can? So would the height stay the same, relative to the radius of the base? Would it be larger? Would it be smaller? Okay. So just like intuitively, if you think about it, well, if the top is open, and you've still got the same amount of surface area to use, then you could make, the base bigger, so you'd have a wider can, probably of a shorter height. And in fact, solving the problem for the open top can, we'll just mention here that it can be shown, okay, that the open top, okay, cylindrical can, having some surface area, kind of capital S square units, and a maximal volume, will always have the dimensions as dimensions. This time, the base radius, which we'll call say r star, is going to be the square root of s, divided by 3 pi units, and the height of the can. Turns out, let's say h star, the height is actually identical to the base radius. Okay, again, square root of s over 3 pi. Okay, and so you could see that in this case, the radius of the base of the open top can is significantly larger than the base radius of the closed top can. Because notice here, under the radical sign, the s is only divided by 3 pi instead of being divided by 6 pi previously. So we have a greater base radius. So let's say this is our r, and so here's the other r, right? And the height of the can is equal to the base radius. Okay, so the h star is equal to r star, where this is our r star. And so here's our can, the dimensions for the open top can of maximal volume. Okay. So it looks something like that. So if it's open top, you want to maximize the volume for a given surface area. You choose the base radius to be the same as the height of the can. For the closed top can, to optimize the volume, you're going to have the diameter of the base, okay, the diameter of the base equal to the height of the can. So this is our final example on applied optimization. So let me know what you think. Thanks for watching. Bye.